Hey everyone! Welcome back to the channel where we dive deep into Earth's most incredible chapters. Tonight we're taking a journey to a time when our planet looked nothing like the world you know today. We're heading back 200 million years to an era that Hollywood loves to dramatize, but the real story is far more fascinating than any movie could capture. We're exploring the Jurassic period, and trust me, what you think you know about this ancient world is just the beginning. Before we start this adventure together, I want you to picture something. Imagine stepping outside your door right now, but instead of the familiar sights around you, you're surrounded by forests so tall, they dwarf modern skyscrapers. The air is thick with humidity, and there's not a single blade of grass in sight. The ground beneath your feet is carpeted with ferns that stretch as far as you can see, and in the distance, something massive is moving through the trees. Something so large that each footstep sends vibrations through the earth. That's the Jurassic period, and it's where we're headed today. So grab your favorite drink, get comfortable, and let's embark on this incredible journey together. And hey, if you enjoy exploring Earth's ancient mysteries with me, go ahead and hit that like button. It really helps the channel reach other curious minds who love learning about our planet's incredible past. Now, when most people hear the word Jurassic, their minds immediately jump to towering dinosaurs with massive teeth and thundering roars. And sure, those creatures were absolutely part of this world, but they were just one piece of an intricate puzzle that was far more complex and beautiful than any single movie franchise could ever capture. The Jurassic period stretched from about 201 million years ago to roughly 145 million years ago. To put that in perspective, if all of human history were compressed into a single day, the entire Jurassic period would span nearly 4 months. This wasn't just some prehistoric backdrop for giant reptiles to stomp around in. This was a living, breathing world with its own weather patterns, its own ecosystems, and its own incredible story of survival and adaptation. It was an Earth in the middle of one of the most dramatic transformations our planet has ever experienced. And every creature that lived during this time had to navigate a world that was constantly changing beneath their feet. The first thing you need to understand about the Jurassic is that this was a greenhouse Earth. There were no polar ice caps, no frozen tundras, and no snow-covered mountains stretching to the horizon. Instead, warmth extended from the equator all the way to what we now call the North and South Poles. Imagine a world where forests grew in Antarctica and where the Arctic Ocean was actually warm enough to support tropical marine life. That was the reality of the Jurassic period. This global warmth wasn't just a minor climate difference. It fundamentally changed how life could exist on our planet. With no ice caps locking away massive amounts of water, sea levels were significantly higher than they are today. Vast shallow seas covered areas that are now dry land, creating thousands of miles of warm, nutrient-rich coastlines, where life could flourish in ways we can barely imagine. The atmosphere itself was different too. Carbon dioxide levels were much higher than what we experience today, sometimes 4 or 5 times higher than pre-industrial levels. This created a greenhouse effect that trapped heat and maintained those warm global temperatures. But it also meant that plants could photosynthesize more efficiently, leading to explosive growth and the creation of some of the most lush and productive ecosystems our planet has ever seen. Picture walking through a Jurassic forest, and the first thing that would strike you is the sheer scale of everything. Conifer trees stretched over 100 feet into the sky, their trunks so massive that it would take several people holding hands to wrap around them. These weren't the familiar pine or spruce trees you might know today, but they're ancient relatives, built to thrive in this warm, humid world. But here's where it gets really interesting. The ground beneath these towering trees wasn't covered with grass. Grasses hadn't evolved yet. Instead, the forest floor was dominated by ferns. Not the small, delicate ferns you might see in a modern garden, but massive fern prairies that stretched for miles. Some of these ferns grew waist-high, creating dense green carpets that covered entire valleys and plains. Mixed throughout these fern prairies were cycads, strange plants that looked like a cross between a palm tree and a pineapple. These sturdy plants had thick trunks topped with crowns of stiff, feathery leaves, and they were everywhere. Some were small and shrub-like, while others grew into impressive trees that dominated the landscape alongside the towering conifers. The diversity of plant life was staggering, but it was organized completely differently than the plant communities we see today. Without flowering plants, which wouldn't appear until later, the Jurassic world was painted in endless shades of green. There were no colorful blooms to break up the monotony, no fruit hanging from branches, and no meadows filled with wildflowers. Instead, reproduction happened through cones, spores, and seeds, creating a world that was lush and productive, but alien in its uniformity. These plant communities weren't just background scenery. They were the foundation that made everything else possible. The incredible abundance of vegetation meant that plant-eating animals could grow to sizes that seem almost impossible today. When you have forests stretching across entire continents and fern prairies that never seem to end, you can support herbivores that need hundreds of pounds of food every single day. And that brings us to the real stars of the Jurassic show, the sauropods. These were the long-necked giants that have captured imaginations for generations, but their real story is far more incredible than their size alone. Creatures like Brachiosaurus, Diplodocus, and Apatosaurus weren't just big, they were perfectly engineered for their world. Their necks, which could stretch over 20 feet long, weren't just for show. They were feeding tools that allowed these animals to browse at different levels of the forest canopy. While one species might feed on the tops of conifer trees, another could sweep through mid-level cycads, and still others could graze on the fern prairies below. This vertical feeding strategy meant that multiple species of these giants could share the same territory without directly competing for food. But here's what really blows my mind about these creatures. They didn't just survive in the Jurassic world, they thrived. Fossil evidence shows us that they lived in herds, traveled together across vast distances, and successfully raised their young in a world full of predators. Their social behaviors were complex, their migration patterns were extensive, and their impact on the landscape was profound. When a herd of sauropods moved through a forest, they didn't just browse quietly and move on. They knocked down trees, opened up clearings in the canopy, and created pathways that other animals could use. Their droppings fertilized the soil and spread seeds across hundreds of miles. In many ways, these giants were ecosystem engineers, actively shaping the world around them just by living their daily lives. Of course, where there were massive plant eaters, there were also predators. The Jurassic gave rise to some of the most formidable hunters our planet has ever seen. Allosaurus and its relatives weren't just random killing machines. They were sophisticated predators with complex hunting strategies and social behaviors that we're only beginning to understand. These predators had to be smart about their hunting. A full-grown sauropod could easily crush or kill an attacking predator, so these hunters had to be strategic. They likely targeted the young, the sick, or isolated individuals. They may have hunted in coordinated groups, using their intelligence and teamwork to bring down prey that no single predator could handle alone. The fossil record gives us tantalizing glimpses of these predator-prey interactions. Bite marks on sauropod bones that match the teeth of Allosaurus, healed wounds that show some attacks were survived, and trackways that seem to show predators following herds across ancient floodplains. Each piece of evidence helps us understand that the Jurassic wasn't a peaceful world of gentle giants, but a dynamic ecosystem where survival required constant vigilance and adaptation. But the land was just half the story. The oceans of the Jurassic were every bit as incredible as the terrestrial ecosystems, and they were filled with creatures that seem almost too fantastic to believe. Marine reptiles had evolved to fill every niche in the ocean, from swift pursuit predators to massive apex hunters that dominated the seas. Ichthyosaurs were the dolphins of the Jurassic world, but they were reptiles, not mammals. These creatures had evolved streamlined bodies that were perfectly adapted for speed and efficiency in the water. Some species grew to enormous sizes, reaching lengths of over 50 feet, while others remained smaller and more agile. Their large eyes gave them exceptional vision in the dim underwater world, and their powerful tails could propel them through the water at incredible speeds. The oceans were also home to plesiosaurs, creatures that looked like nothing alive today. With their 4 powerful flippers and long necks, they moved through the water like underwater flying machines. Some had necks so long they could stretch them out into schools of fish without moving their massive bodies, while others had shorter necks and enormous heads filled with teeth designed for crushing prey. And ruling over all of these marine reptiles were the pliosaurs, apex predators with heads the size of small cars and teeth as long as railroad spikes. These were the undisputed rulers of the Jurassic seas, capable of taking down any other marine animal they encountered. The diversity of life in these ancient oceans was staggering. Ammonites filled the water with their coiled shells, floating through the currents in numbers so vast that their fossils now help us date rock layers around the world. Coral reefs stretched across warm, shallow seas, creating underwater cities that supported countless species of fish, crustaceans, and other marine life. What's truly remarkable about the Jurassic period is how all of these different ecosystems, on land and in the sea, were connected. Rivers carried nutrients from the forests to the oceans, feeding massive blooms of plankton that supported entire marine food webs. Coastal areas became mixing zones where terrestrial and marine ecosystems overlapped, creating unique habitats that supported both land-dwelling and sea-going creatures. The world during this time wasn't static either. This was a period of incredible geological activity, with continents slowly drifting apart and new ocean basins opening up. Volcanic eruptions were common, sometimes covering vast areas with lava and ash, but also creating new land and enriching soils with nutrients that fueled explosive plant growth. All of this activity, both biological and geological, created a world that was constantly changing and evolving. Species had to adapt not just to predators and prey, but to shifting climates, changing landscapes, and volcanic eruptions that could reshape entire regions in a matter of days. As we continue our journey through the Jurassic period, we'll explore how these incredible ecosystems functioned, how the creatures that lived in them survived and thrived, and how this ancient world set the stage for everything that came after. We'll dive deeper into the lives of the giants that ruled the land, explore the incredible diversity of the ancient oceans, and discover how even the smallest creatures played crucial roles in keeping these complex ecosystems running. The Jurassic period wasn't just a chapter in Earth's history, it was a masterpiece of evolution and adaptation, a world so rich and complex that we're still discovering new secrets hidden in its fossil record. So stick around, because we're just getting started on this incredible journey through one of the most fascinating periods our planet has ever experienced. The story of Jurassic plant life gets even more fascinating when you realize that these ancient forests operated on completely different principles than anything we see today. Without grasses to create open meadows or flowering plants to add bursts of color, the entire landscape was structured around layers of green that stretched from the forest floor to the canopy. Imagine walking through one of these ancient forests, and you'd notice something immediately striking about the understory. Instead of the mixed shrubs and wildflowers you might expect in a modern forest, the ground was dominated by horsetails. These weren't the small, delicate plants you might find along a modern riverbank. Jurassic horsetails could grow 30 feet tall, creating dense stands that looked like bamboo forests made of jointed green stems. These towering horsetails thrived in wet areas, stabilizing riverbanks and creating unique habitats that supported countless smaller creatures. Their hollow, segmented stems made distinctive rustling sounds in the wind, and their spore-bearing cones at the top released clouds of reproductive material that drifted on air currents for miles. But perhaps The most alien aspect of Jurassic plant communities was how they reproduced. Without the bright flowers and sweet fruits that attract pollinators in modern ecosystems, these ancient plants relied on wind, water, and primitive insects to spread their genetic material. Conifers released massive clouds of pollen that could drift for hundreds of miles. Ferns scattered microscopic spores that could colonize new territory with incredible speed. Cycads developed massive cones that could weigh hundreds of pounds, filled with seeds protected by tough shells. This reproductive strategy created seasonal rhythms that were completely different from what we experience today. Instead of spring flowers and autumn fruits, Jurassic seasons were marked by spore releases, pollen storms, and the development of enormous seed cones that took years to mature. The efficiency of these plant communities was remarkable. With higher carbon dioxide levels in the atmosphere, photosynthesis was supercharged. Plants could grow faster and larger than their modern counterparts, creating biomass on scales that seem almost impossible today. Some individual trees may have lived for thousands of years, slowly adding ring after ring of growth, until they became living monuments in landscapes that changed around them. This incredible plant productivity created opportunities for herbivores that we can barely comprehend. The sauropods we talked about earlier weren't just lucky to find enough food. They were living in a world specifically designed to support giants. A single brachiosaurus needed to consume somewhere between 400 and 500 pounds of plant material every day. In most modern ecosystems, that would be impossible. But in the Jurassic, with its endless fern prairies and towering conifer forests, there was more than enough vegetation to support multiple species of these giants living side by side. The feeding strategies of these massive herbivores were surprisingly sophisticated. Different species had evolved different approaches to processing all that plant material. Some had long, slender necks that could sweep through vegetation like living vacuum cleaners. Others had shorter, more muscular necks, designed for stripping tough branches and cones from conifer trees. Their teeth tell fascinating stories about their diets. Sauropod teeth weren't designed for chewing the way mammalian herbivores chew today. Instead, they were simple tools for stripping and swallowing. The real processing happened in their enormous guts, where stones called gastroliths helped grind tough plant fibers, and beneficial bacteria broke down cellulose into digestible nutrients. This digestive strategy required massive body cavities, which explains why sauropods had such enormous torsos. They weren't just big for the sake of being big, they were big because they needed room for digestive systems that could process hundreds of pounds of tough plant material every single day. But sauropods weren't the only herbivores in this ancient world. The Jurassic also gave us Stegosaurus and its relatives, creatures that took a completely different approach to surviving in a world full of predators. Where sauropods used size as their primary defense, stegosaurs used armor and weapons. The famous plates running down a stegosaurus's back weren't just for show. These bony structures may have helped regulate body temperature, acting like solar panels that could absorb heat when the animal was cold and radiate heat when it was too warm. But they also served as visual signals, helping individuals recognize their own species and possibly even communicate emotional states to other stegosaurs. The real weapons were at the other end. The spiked tail of a stegosaurus, known informally as a thagomizer, could swing with devastating force. Fossil evidence shows puncture wounds in predator bones that match these spikes perfectly. Proof that these weren't just defensive displays, but actual weapons that could kill or seriously injure attacking predators. Living with these defensive adaptations meant that stegosaurs had to balance mobility with protection. Their heavily armored bodies made them slower than other herbivores, but their weapons made them extremely dangerous to attack. This created an interesting dynamic where predators had to weigh the risks and benefits of every potential hunt. The smaller herbivores of the Jurassic developed different survival strategies altogether. Ornithopods, the group that would eventually give rise to hadrosaurs in the Cretaceous, were built for speed and agility. These creatures had powerful hind legs, flexible spines, and beaked mouths that could efficiently process the low-growing vegetation that larger herbivores couldn't reach. Their social behaviors were likely complex, with herding strategies that helped protect individuals from predators. Fossil trackways show groups of these animals moving together across ancient landscapes, sometimes with juveniles protected in the center of the group, surrounded by watchful adults. But predation pressure in the Jurassic wasn't just about giant theropods like Allosaurus. The ecosystems were full of smaller, more specialized hunters that filled different niches in the food web. Some theropods were no bigger than modern wolves, but they were perfectly adapted for hunting smaller prey, pursuing ornithopods through fern thickets, or ambushing unwary cycads browsers. These smaller predators were often more agile and possibly more intelligent than their larger cousins. They had to be because their prey was fast and alert. Fossil evidence suggests that some of these smaller theropods may have hunted in coordinated groups, using teamwork to bring down prey that individual hunters couldn't handle alone. The diversity of predatory strategies in Jurassic ecosystems was remarkable. Some theropods were built for pure speed, chasing down fast-moving prey in open areas. Others were ambush predators, using stealth and surprise to overcome their victims. Still others were scavengers, following herds and waiting for opportunities to feed on the weak, injured, or dead. This predatory diversity created what ecologists call a complex trophic web, where energy flowed through multiple pathways from plants to herbivores to various levels of carnivores. No single predator dominated completely, and no single prey species was without defenses. The result was a dynamic balance that could absorb disruptions and maintain stability over millions of years. The success of these terrestrial ecosystems depended on more than just the big players we tend to focus on. Insects were absolutely crucial to Jurassic ecosystems, though their roles were different from what we see today. Without flowering plants to pollinate, Jurassic insects filled other ecological niches. They were decomposers, breaking down dead plant and animal material and recycling nutrients back into the soil. They were prey for countless smaller vertebrates, and they were pollinators for the few plant groups that had evolved relationships with insect partners. Dragonflies patrolled wetlands and forest clearings, some with wingspans larger than modern species. Beetles crawled through leaf litter and burrowed into decaying logs. Early relatives of ants and wasps built complex social colonies underground. The constant hum of insect activity provided a soundtrack to Jurassic life that would have been as constant and pervasive as it is in tropical regions today. These insects supported populations of small vertebrates that often get overlooked in discussions of Jurassic life. Early mammals, no larger than modern shrews and rats, scurried through the underbrush, feeding primarily. They were nocturnal by necessity, avoiding the giants that rule on insects and other small prey. But they were already developing the characteristics that would eventually make mammals successful. Their teeth were more specialized than reptilian teeth, allowing more efficient processing of food. Their metabolisms were faster, giving them more energy for activity, but requiring them to eat more frequently. And most importantly, they were developing better temperature regulation, using fur for insulation, and maintaining stable body temperatures that allowed them to remain active when reptiles became sluggish. Amphibians also played important roles in Jurassic ecosystems, particularly in wetland environments. Frogs and salamanders thrived in the warm, humid conditions, their calls echoing across marshes and riverbanks just as they do today. They served as important links in food webs, consuming enormous quantities of insects while providing food for reptiles, early mammals, and larger amphibians. The presence of these smaller animals created layers of complexity in Jurassic ecosystems that made them incredibly resilient. When larger animals were affected by environmental changes, populations of smaller creatures could expand to fill vacant niches. When climate fluctuations reduced plant productivity in some areas, animals could shift their diets or move to more favorable locations. This resilience was tested repeatedly throughout the Jurassic period by volcanic eruptions, climate shifts, and the ongoing breakup of the supercontinent Pangaea. Each of these events created challenges for living creatures, but they also created opportunities. New habitats opened up as continents drifted apart. Volcanic soils provided nutrient-rich growing conditions for plants. Climate changes favored some species while challenging others, driving evolutionary innovation and adaptation. The result was a world in constant flux, where species were continuously adapting to new conditions and new opportunities. This dynamic environment fostered evolutionary experimentation on a scale that we rarely see in more stable periods of Earth's history. It was during the Jurassic that many of the major animal groups we recognize today first appeared or underwent major evolutionary radiations that set the stage for their later success. Understanding how these ancient ecosystems functioned gives us insights not just into the past, but into how complex biological systems respond to environmental change. The lessons learned from studying Jurassic life have profound implications for understanding how modern ecosystems might respond to current climate changes and other environmental pressures. As we continue exploring this incredible ancient world, we'll delve even deeper into the specific adaptations that made Jurassic life so successful, examine how these creatures interacted with each other and their environment, and discover how the legacy of the Jurassic period continues to influence life on Earth today. The skies above this ancient world tell their own remarkable story, one that's often overshadowed by the giants walking below. When we look up into a Jurassic sky, we're witnessing one of the most important evolutionary experiments in Earth's history: the conquest of the air by vertebrate life. Pterosaurs had already claimed the skies as their domain, and by the Jurassic period, they had evolved into an incredible array of forms. These weren't the massive giants that would dominate Cretaceous skies, but they were perfectly adapted for their world. Some were no larger than sparrows, darting between branches to catch insects with precision that would make modern birds envious. Others had wingspans that stretched 15 feet or more, soaring over coastlines and inland seas with an efficiency that came from millions of years of refinement. What made pterosaurs so successful wasn't just their ability to fly, it was how they integrated flight into every aspect of their lives. Their wings weren't just for transportation, they were tools for hunting, for display, and for survival. Some species could fold their wings and walk on all fours when they landed, using their wing fingers as additional limbs for climbing or maneuvering on the ground. The diversity of pterosaur lifestyles was staggering. Coastal species had long, narrow wings perfect for gliding over ocean swells, using air currents rising off the waves to stay aloft for hours with minimal energy expenditure. These maritime pterosaurs had sharp, pointed beaks filled with needle-like teeth, perfect for snatching fish from just beneath the surface of the water. Inland pterosaurs developed different specializations entirely. Forest-dwelling species had broader, more maneuverable wings that could navigate between trees and through dense vegetation. Their diets ranged from insects to small vertebrates, and some may have even fed on fruits and seeds from cycads and conifers. But the Jurassic skies weren't exclusively pterosaur territory. This was also the period when something truly revolutionary was happening in the evolutionary laboratory of life. Small theropod dinosaurs were beginning their transformation into birds, and the first tentative experiments in feathered flight were taking place. Archaeopteryx, discovered in the limestone quarries of Germany, represents one of the most important fossils ever found. This creature had the teeth and long bony tail of a dinosaur, but it also had feathers and wings. It was a living bridge between two worlds, showing us exactly how one group of animals can transform into something completely different over time. The flight capabilities of these early birds were probably quite limited compared to modern species. They likely couldn't soar like pterosaurs or perform the complex aerial maneuvers we see in contemporary birds. Instead, they probably used their wings for gliding between trees, for escaping predators, and for reaching food sources that ground-dwelling animals couldn't access. But what they lacked in flight performance, they made up for in potential. The feathered wing design would eventually prove superior to the membrane wings of pterosaurs in terms of control, efficiency, and versatility. Feathers could be individually controlled, allowing for precise adjustments in lift and drag. They could be molted and replaced if damaged. And they provided insulation that helped maintain body temperature during flight. The coexistence of pterosaurs and early birds in Jurassic skies created a fascinating dynamic. These two groups were solving the same basic problem, how to fly, but they were doing it in fundamentally different ways. Pterosaurs had evolved from reptiles and maintained many reptilian characteristics, while birds were evolving from dinosaurs and carried forward many dinosaurian traits. This aerial ecosystem was supported by an abundance of flying insects that provided food for both pterosaurs and early birds. Dragonflies with wingspans larger than your hand patrolled wetlands and forest clearings. Primitive flies buzzed around decomposing plant matter and animal carcasses. Early ect groups relatives of modern inns filled the air with a constant symphony of buzzing, chirping, and humming. The interactions between flying vertebrates and insects created complex food webs in 3 dimensions. Small pterosaurs competed with early birds for insect prey, while larger pterosaurs focused on fish and small vertebrates. Some pterosaurs may have even fed on eggs and nestlings, creating predation pressure that influenced the evolution of nesting behaviors in other species. The ability to fly also meant that these creatures could exploit resources across vast distances. A pterosaur could nest on coastal cliffs, but feed in inland wetlands hundreds of miles away. Early birds could follow seasonal migrations of insects, or take advantage of temporary food sources, like mass emergences of flying insects. This mobility had profound effects on ecosystem dynamics. Flying creatures could transport nutrients between habitats that were otherwise isolated. They could spread seeds and spores across continents. They could even transport smaller organisms, like insects and spiders, to new territories where they might establish new populations. The evolution of flight during the Jurassic also demonstrates one of the most important principles in evolutionary biology: convergent evolution. When similar environmental pressures act on different groups of organisms, they often evolve similar solutions. The fact that pterosaurs, early birds, and insects all independently evolved powered flight shows just how advantageous this ability was in Jurassic ecosystems. But flight wasn't the only evolutionary experiment happening during this period. The Jurassic was a time of incredible diversification across all groups of organisms, from the largest sauropods to the smallest invertebrates. This diversification was driven by the breakup of Pangea, which created new habitats and isolated populations that could evolve independently. As the supercontinents slowly pulled apart, populations of animals and plants became separated by newly formed ocean barriers. These isolated populations faced different environmental challenges and opportunities, leading to rapid evolutionary changes. Over millions of years, these separated populations diverged into distinct species, each adapted to their particular corner of the world. This process of geographic isolation and evolutionary divergence was particularly important for dinosaurs. Early in the Jurassic, dinosaur faunas around the world were relatively similar, but as continents drifted apart, regional differences began to emerge. By the end of the period, dinosaur communities in different parts of the world had developed their own unique characteristics. The same process affected marine life as new ocean basins opened up. The Tethys Sea, which separated the northern and southern landmasses, became a highway for marine dispersal, but also a barrier that separated populations and promoted speciation. Marine reptiles in different ocean basins began to evolve distinct characteristics, leading to the incredible diversity we see in the fossil record. Plant evolution during the Jurassic was equally dramatic, though perhaps less obvious to casual observers. The period saw the continued diversification of gymnosperms, the group that includes conifers and cycads. New families and genera appeared, each adapted to specific environmental conditions or ecological niches. Some conifers evolved massive trunks and towering heights, competing for light in dense forests. Others remained smaller but developed specialized adaptations for surviving in drier or more challenging environments. Cycads experimented with different growth forms, from small shrub-like species to impressive tree-like forms that could compete with conifers for space and light. The absence of flowering plants during the Jurassic meant that other plant groups had opportunities that would later be filled by angiosperms. Ferns reached sizes and levels of dominance that seem almost impossible today. Some tree ferns grew to heights of 60 feet or more, creating their own forest canopies in wetland environments. These plant communities supported incredibly complex food webs that extended from the soil to the treetops. Decomposer organisms broke down fallen leaves and dead wood, releasing nutrients that fed new growth. Herbivorous insects consumed living plant tissue, transferring energy to insectivorous predators. Large herbivorous dinosaurs browsed on everything from ground-level ferns to the highest conifer branches, their feeding activities shaping the structure of plant communities. The efficiency of these ecosystems was remarkable. Energy flowed from sunlight through plants to herbivores to predators with minimal waste. Dead organic matter was quickly recycled by decomposers, ensuring that nutrients remained available for new growth. The warm, humid climate meant that biological processes operated at high efficiency year-round, supporting levels of productivity that are difficult to achieve in modern temperate ecosystems. This productivity supported not just the famous large dinosaurs, but entire communities of smaller organisms that are often overlooked. Small theropod dinosaurs, no bigger than chickens, darted through underbrush, pursuing insects and small vertebrates. Early mammals maintained active lifestyles despite their small size, their high metabolisms allowing them to exploit resources that were unavailable to reptiles with slower metabolisms. Aquatic environments were equally productive and diverse. Rivers and lakes teemed with fish, amphibians, and aquatic reptiles. Freshwater ecosystems supported their own food webs, from microscopic plankton to large predatory reptiles. These freshwater communities were connected to terrestrial ecosystems through the animals that moved between land and water, transferring energy and nutrients between these different habitats. The integration of terrestrial, freshwater, and marine ecosystems during the Jurassic created a global biosphere of unprecedented complexity. Nutrients cycled between land and sea through rivers and coastal interactions. Animals migrated between different habitats seasonally or as part of their life cycles. Even the atmosphere was affected by biological processes, with vast forests influencing local and regional climate patterns. This level of ecosystem integration meant that changes in one part of the system could have cascading effects throughout the biosphere. A volcanic eruption might destroy forests in one region, but the ash and nutrients it deposited could enhance productivity in distant areas. Climate changes that affected ocean temperatures could influence precipitation patterns on land, altering the distribution and productivity of terrestrial plant communities. The resilience of Jurassic ecosystems came from this complexity and integration. When local disruptions occurred, organisms could often find refuge in other habitats or rely on resources from unaffected areas. The high level of connectivity meant that recovery from disturbances could be rapid, with organisms recolonizing affected areas from surviving populations elsewhere. This resilience was tested repeatedly throughout the Jurassic by natural disasters, climate fluctuations, and ongoing geological changes. Each test refined the system, eliminating less adaptable species and favoring those that could respond flexibly to changing conditions. The result was a biosphere that was both stable enough to persist for tens of millions of years and dynamic enough to continue evolving and adapting. Understanding how these ancient ecosystems functioned provides valuable insights into the principles that govern all complex biological systems. The lessons learned from studying Jurassic life help us understand how organisms interact with each other and their environment. how ecosystems respond to environmental change, and how evolution shapes the diversity and complexity of life on Earth. As we continue our exploration of this remarkable period, we'll delve deeper into the specific mechanisms that allowed Jurassic life to thrive, examine the fossil evidence that reveals these ancient secrets, and discover how the innovations of the Jurassic period continue to influence life on our planet today. The story of the Jurassic is far from over. It's written into the DNA of every bird that flies overhead and every tree that reaches toward the sun. The interconnected nature of Jurassic ecosystems becomes even more fascinating when we examine how the breakup of Pangaea was reshaping the very foundation of life on Earth. Picture the supercontinent as a massive jigsaw puzzle that was slowly coming apart, with each piece carrying its own cargo of plants and animals into an uncertain future. This continental drift wasn't happening quickly by human standards. We're talking about movements measured in centimeters per year, rates so slow that thousands of generations of dinosaurs lived and died without noticing any change. But over the millions of years of the Jurassic period, these tiny movements accumulated into massive transformations that would reshape the entire planet. As Pangaea split apart, it created something that hadn't existed for hundreds of millions of years: new ocean basins. The Atlantic Ocean was just beginning to form, starting as narrow rifts that slowly filled with seawater. These early Atlantic waters were warm and shallow, perfect nurseries for marine life that would eventually spread across what would become one of Earth's largest oceans. The Tethys Sea, wedged between the northern and southern portions of the splitting continent, became one of the most biologically important bodies of water in Earth's history. This tropical ocean stretched from what would become the Western Atlantic all the way to the areas that would later form parts of Asia. Its warm, shallow waters created perfect conditions for coral reefs that supported incredibly diverse marine communities. But these reefs weren't just beautiful underwater gardens, they were three-dimensional cities teeming with life. Coral polyps built limestone structures that created complex mazes of caves, tunnels, and chambers. Every surface was alive with something. Sponges filtered water through their porous bodies. Crustaceans scuttled across the reef floor with their claws clicking against the limestone. And countless species of fish darted through the coral branches like living jewels. The reef communities supported food webs of staggering complexity. Tiny organisms at the base of the food chain converted sunlight and nutrients into living tissue that fed slightly larger creatures, which in turn supported predators, which supported larger predators, all the way up to the massive marine reptiles that ruled these ancient seas. Ichthyosaurs had become the supreme ocean predators by the Jurassic, and their success story is one of evolution's most elegant solutions to the challenge of aquatic life. These reptiles had developed body plans that were remarkably similar to modern dolphins, despite being completely unrelated. Their streamlined bodies could slice through water with minimal drag, while their powerful tails provided the propulsion needed for high-speed chases. Some ichthyosaurs grew to enormous sizes, reaching lengths that would dwarf modern killer whales. These giants had eyes the size of dinner plates, adaptations that allowed them to hunt in the dim depths of ancient oceans. Their vision was so acute that they could spot prey from incredible distances, giving them a crucial advantage in the three-dimensional hunting ground of the open ocean. But not all ichthyosaurs were giants. The group had diversified into species ranging from dolphin-sized hunters to massive deep-sea predators. Some specialized in catching fast-moving fish, while others focused on squid-like creatures that they could pursue into the depths. This diversity meant that ichthyosaurs could exploit nearly every marine niche, from shallow coastal waters to the open ocean. Sharing these waters were the plesiosaurs, creatures so unusual that they challenge our imagination even today. With their 4 flipper-like limbs and impossibly long necks, they moved through the water like nothing alive in our modern oceans. Some species had necks that contained more than 70 vertebrae. allowing them to stretch their heads far from their bodies to investigate crevices in reefs or dart into schools of fish with lightning speed. The longest-necked plesiosaurs could keep their massive bodies hidden while extending their heads into new hunting territories. Imagine being a fish in a Jurassic reef and having a head the size of a horse suddenly appear from around a coral formation, supported by a neck that seemed to go on forever. This hunting strategy was so effective that some plesiosaur species dominated their marine environments for millions of years. But the apex predators of these ancient seas were the pliosaurs, creatures that combined the body plan of plesiosaurs with the predatory instincts of modern great white sharks. These monsters had shortened their necks and enlarged their heads until they became living battering rams, equipped with teeth that could crush bone. Some pliosaurs reached lengths of 50 feet or more, with skulls alone measuring over 6 feet long. The bite force of these creatures was astronomical, easily capable of crushing the shells of large ammonites or the bones of other marine reptiles. They were the undisputed rulers of Jurassic oceans, and their presence influenced the behavior and evolution of every other marine animal. The fear they inspired can still be seen in the defensive adaptations of their prey species, from the reinforced shells of ammonites to the speed and agility of smaller marine reptiles. Ammonites deserve special attention because they were perhaps the most successful marine invertebrates of their time. These relatives of modern squid and octopuses had solved the challenge of ocean life by building portable homes in the form of coiled shells. These shells weren't just protection, they were sophisticated buoyancy control systems that allowed ammonites to adjust their depth in the water column with precision. The diversity of ammonite shell shapes was incredible, ranging from tightly coiled spirals to loose, almost straight forms. Each shape represented a different lifestyle and ecological niche. Some were built for speed, with streamlined shells that could slice through water efficiently. Others were designed for maneuverability, with wide, flat shells that provided stability in turbulent waters. The internal structure of ammonite shells was an engineering marvel. Chambers filled with gas or fluid could be adjusted to control buoyancy, while the complex suture patterns where chamber walls met the outer shell provided incredible strength without excessive weight. Some of these suture patterns were so intricate that they look almost like abstract art, testament to the sophisticated solutions evolution can produce. These marine ecosystems were constantly changing as new seaways opened and existing ones shifted. Ocean currents that had flowed in the same patterns for millions of years suddenly found new pathways as continents drifted apart. These changing currents redistributed heat, nutrients, and marine life across the globe, creating opportunities for some species while challenging others. The warm temperatures that characterized the Jurassic meant that ocean currents behaved differently than they do today. Without cold polar waters to drive deep circulation patterns, the oceans mixed more slowly and retained heat more effectively. This created stable, warm conditions that extended from the tropics almost to the poles, supporting marine life in regions that are now too cold for coral reefs. Volcanic activity along the spreading mid-ocean ridges added another dynamic element to these marine systems. Underwater eruptions created new sea floor and released nutrients that supported blooms of plankton. These plankton blooms fed everything from tiny fish to massive filter-feeding marine reptiles, creating temporary abundances that could support entire food webs. The interaction between land and sea during the Jurassic was particularly important because sea levels were much higher than today. Vast areas of what are now continents were covered by shallow seas, creating thousands of miles of coastline where terrestrial and marine ecosystems could interact. These coastal environments were incredibly productive, combining nutrients from terrestrial runoff with the biological productivity of marine systems. Estuaries and lagoons provided nursery areas for marine animals while supporting their own unique communities of plants and animals adapted to changing salinity levels. Pterosaurs took full advantage of these coastal environments, with many species specializing in marine prey. Their ability to fly meant they could exploit resources across vast areas of ocean, following schools of fish or taking advantage of seasonal abundance in different regions. Some pterosaur species may have spent most of their lives over the ocean, coming to land only to breed and raise their young. The fossil record from these coastal environments is particularly rich, preserving not just marine fossils, but also evidence of the interactions between land and sea. Dinosaur trackways have been found in ancient tidal flat deposits, showing that these giants regularly visited coastal areas, possibly to drink from freshwater springs or to take advantage of mineral-rich sediments. Even terrestrial plants were influenced by their proximity to the sea. Coastal forests had to adapt to salt spray and occasional flooding, developing specialized root systems and leaf structures that could tolerate these challenging conditions. These coastal plant communities supported their own unique assemblages of herbivorous dinosaurs and smaller animals. The integration of terrestrial and marine systems during the Jurassic created feedback loops that influenced climate and ocean chemistry on a global scale. Forests influenced local rainfall patterns, which affected the amount of fresh water flowing into coastal seas. Ocean temperatures influenced atmospheric circulation patterns, which affected precipitation on land. This interconnectedness meant that changes in one part of the system could have far-reaching effects. A period of increased volcanic activity might release carbon dioxide that warmed the oceans, which could intensify the water cycle and increase rainfall on land, which could enhance forest growth and change the amount of nutrients flowing into marine systems. Understanding these complex interactions helps us appreciate why Jurassic ecosystems were so stable and productive over such long periods of time. The integration of land and sea created multiple pathways for energy and nutrient cycling, making the entire system more resilient to local disturbances. The legacy of these Jurassic marine systems can still be seen today in the limestone formations that were built by coral reefs, in the oil deposits that formed from marine plankton, and in the evolutionary relationships among modern marine animals. Many of the basic body plans and ecological strategies that evolved in Jurassic oceans continue to influence marine life today. As we continue our journey through this remarkable period, we'll explore how these complex systems responded to environmental changes, how they influenced the evolution of life on land, and how the innovations that first appeared in Jurassic ecosystems continue to shape our modern world. The story of the Jurassic is ultimately a story about connections, about how life in all its forms works together to create systems of incredible beauty, complexity, and resilience. The climate systems that drove all of this biological activity were unlike anything we experience today, operating on principles that created a fundamentally different kind of planet. Without polar ice caps to regulate global temperatures, the Jurassic world experienced what scientists call a greenhouse climate, where warmth extended from the equator to regions that are now frozen wastelands. This greenhouse effect wasn't just about higher average temperatures, it was about the elimination of extreme cold anywhere on the planet. Even areas that would today be covered in ice and snow supported lush forests filled with dinosaurs and other tropical life forms. The temperature gradient between the equator and the poles was much smaller than it is today, creating a more uniform global climate. The atmospheric composition was dramatically different as well, with carbon dioxide levels that were several times higher than pre-industrial levels. This enhanced greenhouse effect was maintained by constant volcanic activity associated with the breakup of Pangaea, which continuously added carbon dioxide to the atmosphere. The result was a self-reinforcing system where warmth promoted biological activity, which in turn influenced atmospheric composition. Rainfall patterns in this greenhouse world were controlled by different mechanisms than we see today. Without the temperature contrasts that drive modern weather systems, precipitation was dominated by monsoon-like patterns that brought seasonal deluges to some regions while leaving others relatively dry. These patterns created distinct wet and dry seasons that profoundly influenced the behavior and evolution of terrestrial life. During the wet seasons, Vast areas that had been parched and brown would burst into green life almost overnight. Rivers that had been reduced to trickles became raging torrents, carrying nutrients and sediments across the landscape. Plant growth exploded, providing abundant food for herbivores that had endured months of scarcity. The dry seasons were equally dramatic, testing the survival skills of every organism. Water sources dried up, vegetation withered, and animals were forced to migrate vast distances in search of resources. These seasonal migrations may have been some of the greatest animal movements in Earth's history, with herds of sauropods traveling hundreds or even thousands of miles following the rains. These climatic extremes drove evolutionary innovations that we can still see in the fossil record. Plants developed strategies for surviving extended dry periods, from deep root systems that could tap groundwater to specialized storage organs that could hold water and nutrients through lean times. Animals evolved behavioral and physiological adaptations that allowed them to cope with feast or famine cycles. The absence of polar ice had another crucial effect on global climate systems. It changed how ocean currents circulated heat around the planet. Today, cold, dense water sinking at the poles drives deep ocean circulation that helps distribute heat globally. In the Jurassic, with warm water extending almost to the poles, circulation patterns were gentler and less effective at mixing the oceans. This reduced circulation meant that the oceans stratified more strongly, with warm surface waters sitting on top of cooler deep waters, with limited mixing between them. This stratification affected marine ecosystems by concentrating nutrients in certain layers and creating oxygen-depleted zones in the deep ocean. The warm, stable climate also meant that weather systems operated differently than they do today. Storms were often more intense but less frequent, building up over warm ocean waters and then unleashing incredible amounts of energy when they made landfall. These superstorms could reshape entire coastlines and river systems in a matter of days. Lightning from these massive storm systems may have been crucial for maintaining soil fertility in some regions, as electrical discharges convert atmospheric nitrogen into forms that plants can use. The constant rumble of thunder would have been a familiar sound across much of the Jurassic landscape, punctuating the calls of dinosaurs and the rustle of wind through ancient forests. The interaction between climate and topography created an incredible diversity of local environments across the Jurassic world. Mountain ranges created rain shadows that supported desert communities, while river valleys became corridors of lush vegetation that could support massive herbivore populations. Coastal areas enjoyed moderated temperatures and consistent moisture, while continental interiors experienced more extreme seasonal variations. These climatic patterns influenced every aspect of life, from the timing of reproduction to the structure of food webs. Many animals probably timed their breeding cycles to coincide with seasonal abundance, ensuring that young were born when food was most plentiful. Plant flowering and fruiting cycles would have been synchronized with rainfall patterns, creating pulses of resources that rippled through entire ecosystems. The stability of this greenhouse climate over millions of years allowed ecosystems to develop levels of complexity and integration that would be impossible under more variable conditions. Species had time to evolve intricate relationships with each other and with their physical environment, creating webs of interdependence that made the entire system more resilient and productive. This climatic stability also allowed for the evolution of the gigantic body sizes that characterize Jurassic life. Large animals have more stable internal temperatures and can better survive temporary resource shortages, but they also require consistent environmental conditions to maintain their populations. The predictable warmth and seasonal abundance of the Jurassic provided exactly the conditions needed for giants to thrive. Understanding Jurassic climate systems gives us insights into how Earth's climate can operate under very different conditions than we experience today. It shows us that our current Ice Age climate, with its polar ice caps and steep temperature gradients, is actually unusual in Earth's history. For most of the past 500 million years, Earth has been warmer and more uniform in temperature than it is today. The transition from the greenhouse conditions of the Jurassic to the more variable climate of later periods would eventually challenge many of the species that had evolved under stable conditions. But during their time, these climate systems supported some of the most spectacular and successful ecosystems in Earth's history, creating a world of abundance that sustained giants for over 50 million years. As we near the end of our exploration of this incredible period, we'll examine how all of these systems, biological, geological, and climatic, work together to create the unique world of the Jurassic, and how the legacy of this remarkable time continues to influence our planet today. The volcanic forces that shaped the Jurassic world were far more than just occasional disruptions to an otherwise peaceful planet. These were constant, creative forces that literally built the stage upon which all of this incredible life performed. As Pangaea continued its slow-motion breakup, massive rifts opened across the supercontinent, and from these wounds in the Earth's crust poured forth the raw materials of new worlds. Picture standing near one of these ancient rift valleys during an active eruption. The ground would tremble beneath your feet as magma forced its way upward through miles of solid rock. When it finally broke through, fountains of molten lava would shoot hundreds of feet into the air, painting the sky in shades of orange and red that no modern volcano could match. The sound would be indescribable, a combination of roaring, hissing, and crackling that could be heard for hundreds of miles. These weren't isolated events happening in remote locations. The Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history, was actively forming during the early Jurassic. This massive outpouring of lava-covered areas that would eventually become parts of 4 different continents, creating basalt flows that in some places were over a mile thick. The immediate effects of these eruptions were devastating to local ecosystems. Forests that had grown for thousands of years were buried under hundreds of feet of lava in a matter of days. Rivers were dammed by cooling rock, creating temporary lakes that would later drain in catastrophic floods. Ash clouds blocked out the sun for months at a time, creating artificial winters that challenged even the most adaptable species. But here's what makes the Jurassic volcanic activity so fascinating from an ecological perspective. Life didn't just survive these catastrophes, it thrived because of them. The ash and lava that destroyed existing ecosystems also created incredibly fertile soils that would support explosive plant growth once conditions stabilized. Within decades of a major eruption, the scorched landscape would begin to turn green again. Ferns, with their ability to spread rapidly through wind-dispersed spores, were typically the first colonizers of volcanic soils. These pioneer species would stabilize the ground and begin the process of soil development that would eventually support entire forests. The minerals released by weathering volcanic rock provided nutrients that were often scarce in other environments. Potassium, phosphorus, and trace elements essential for plant growth were abundant in volcanic soils, creating conditions where vegetation could grow larger and more luxuriously than in non-volcanic areas. This pattern of destruction and renewal created a mosaic of habitats across the Jurassic landscape. At any given time, some areas would be experiencing the immediate aftermath of eruptions, while others would be in various stages of ecological recovery. This diversity of habitat types supported different communities of plants and animals, contributing to the overall biodiversity of Jurassic ecosystems. The volcanic activity also had profound effects on global climate that extended far beyond the immediate areas of eruption. The massive amounts of carbon dioxide released by Jurassic volcanoes helped maintain the greenhouse conditions that characterized the period. Without this constant input of greenhouse gases, the warm global climate that supported tropical vegetation at high latitudes would not have been possible. But volcanic emissions weren't just carbon dioxide. Eruptions also release sulfur dioxide and other compounds that could have cooling effects by blocking sunlight and forming reflective particles in the atmosphere. This created a complex balance where volcanic activity could both warm and cool the climate depending on the specific mix of gases and particles released. The timing and location of volcanic activity influenced ocean circulation patterns as well. When lava flows reached the sea, they created new coastlines and underwater features that affected how ocean currents moved heat around the planet. The formation of new ocean basins as continents drifted apart created entirely new circulation patterns that would influence global climate for millions of years. Marine ecosystems were particularly affected by underwater volcanic activity. When eruptions occurred on the seafloor, they released nutrients that could support massive blooms of plankton, the microscopic organisms that form the base of marine food webs. These nutrient pulses could cascade up through entire ecosystems, supporting everything from small fish to giant marine reptiles. The constant geological activity of the Jurassic also influenced the preservation of fossils in ways that continue to benefit paleontologists today. Volcanic ash provides ideal conditions for fossilization, quickly burying organisms and sealing them away from decay and scavenging. Some of our most detailed fossils from this period come from deposits where volcanic activity preserved entire ecosystems in remarkable detail. Earthquakes were another constant feature of this geologically active world. As tectonic plates shifted and continents drifted apart, the ground frequently shook with tremors that could be felt across vast distances. These earthquakes reshaped river courses, created new lakes and wetlands, and occasionally triggered landslides that could bury entire valleys. For the animals living through these events, earthquakes would have been part of the normal background of life, no more unusual than storms or seasonal changes. Herds of dinosaurs would have felt the ground tremble beneath their feet and instinctively moved away from unstable areas, just as modern animals do in earthquake-prone regions. The geological instability of the Jurassic created evolutionary pressures that favored adaptability and mobility. Species that could quickly relocate when their habitats were destroyed by volcanic activity or earthquakes had significant survival advantages over those that were more specialized for specific environmental conditions. This geological dynamism also created opportunities for rapid evolutionary change. When populations were separated by new rift valleys or mountain ranges, they could evolve independently and develop into distinct species. The breakup of Pangaea accelerated this process by creating physical barriers between populations that had previously been able to interbreed. The mineral wealth created by Jurassic volcanic activity continues to influence human civilization today. Many of the world's most important ore deposits were formed during this period of intense geological activity. The copper, gold, and other metals that are essential to modern technology often trace their origins back to Jurassic magmatic processes. The sedimentary rocks that formed from the erosion of Jurassic volcanic mountains now contain some of our most important fossil fuel deposits. The organic matter that was buried and preserved in these sediments eventually became the oil and gas that powers much of our modern world. Understanding the role of volcanic activity in Jurassic ecosystems also provides insights into how life might respond to similar geological events today. The resilience shown by Jurassic life forms in the face of massive volcanic disruptions demonstrates the incredible capacity of biological systems to adapt and recover from even catastrophic changes. The patterns of ecological succession that followed Jurassic eruptions, with pioneer species quickly colonizing disturbed areas and gradually being replaced by more complex communities, are still visible in how ecosystems recover from volcanic activity today. Modern ecological restoration efforts often follow principles that were first demonstrated in these ancient post-eruption environments. As we continue to explore the incredible complexity of Jurassic life, it becomes clear that the geological forces shaping the planet were not separate from biological processes, but were intimately connected to them. The Earth was not simply a stage upon which life performed, but an active participant in the evolutionary drama, constantly creating new challenges and opportunities that drove the incredible diversity and innovation we see in the fossil record. The legacy of Jurassic geological activity extends far beyond the fossils and rock formations it left behind. The continental configurations established during this period continue to influence global climate patterns today. The ocean basins that began forming as Pangaea broke apart still control how heat and nutrients circulate through our modern oceans. The mountain ranges uplifted by Jurassic tectonic activity continue to influence weather patterns and create the diverse topography that supports different types of ecosystems around the world. Even the soil chemistry in many regions still reflects the influence of ancient volcanic activity that occurred over 150 million years ago. This deep connection between geological and biological processes reminds us that understanding Earth's history requires looking at both the rocks and the fossils, both the physical processes that shaped ancient landscapes and the living creatures that inhabited them. The Jurassic period was not just about dinosaurs. It was about an entire Earth system operating under conditions very different from today, creating opportunities for life to experiment with forms and strategies that would never again be possible. The volcanic forces that seemed so destructive in the short term were actually creative forces that built new land, enriched soils, and created the environmental diversity that supported the incredible abundance of Jurassic life. This paradox of destruction and creation is one of the most important lessons we can learn from studying this remarkable period in Earth's history. As we prepare to conclude our journey through the Jurassic world, we'll examine how all of these forces, biological and geological, climate and chemistry, work together to create ecosystems of unprecedented complexity and beauty, and how the innovations first tested during this incredible period continue to influence life on Earth today. The story of how life and death played out in this ancient world reveals patterns that are both beautiful and brutal in their simplicity. Every creature, from the smallest insect to the most massive sauropod, lived according to rules that were written not in stone, but in the constant dance between predator and prey, between abundance and scarcity, between survival and extinction. Understanding these dynamics requires us to think like detectives, piecing together clues from fossils that tell stories of individual moments frozen in time. A bite mark on a sauropod bone speaks of an encounter between hunter and prey that played out 150 million years ago. A trackway preserved in ancient mud shows us a predator following a herd across a floodplain, the distance between footprints telling us whether the chase was leisurely or desperate. The balance between different groups of animals during the Jurassic created what ecologists call a stable equilibrium, but it was stability built on constant motion. Herbivore populations grew until they pressed against the limits of available vegetation, then predation and resource competition would bring them back into balance. Predator numbers rose and fell in response to prey availability, creating cycles that could span thousands of years. These population cycles were complicated by the unpredictable effects of volcanic eruptions, climate fluctuations, and the ongoing geological changes that constantly reshaped habitats. A volcanic eruption that destroyed a forest might temporarily reduce herbivore populations in that region, which would force predators to either migrate to new hunting grounds or switch to different prey species. The fossil record shows us that Jurassic ecosystems had remarkable resilience in the face of these disruptions. When local populations crashed due to environmental disasters, they could be replenished by migration from unaffected areas. When entire species disappeared from certain regions, ecological niches didn't remain empty for long before being filled by other species that could exploit the same resources. This resilience was built on diversity. The incredible variety of plant and animal species in Jurassic ecosystems meant that there were multiple ways for energy to flow through food webs. If one species of plant became scarce, herbivores could switch to alternatives. If one type of prey disappeared, predators could adapt their hunting strategies to target different species. The success of this system is evident in its longevity. For over 50 million years, these complex ecosystems maintained their basic structure while constantly evolving and adapting to changing conditions. New species appeared and old ones disappeared, but the fundamental relationships between plants and herbivores, herbivores and predators, predators and scavengers remained stable. Social behaviors played crucial roles in this balance. The herding behaviors of sauropods weren't just random groupings of animals. They were sophisticated survival strategies that reduced individual risk while maximizing feeding efficiency. A herd could post sentries while others fed, coordinate movement across vast distances, and protect vulnerable young from predators. Predators developed their own social strategies in response. Some species may have hunted cooperatively, using teamwork to bring down prey that individual hunters couldn't handle. Others specialized in different hunting techniques, with some focusing on ambush tactics, while others relied on pursuit and endurance. The smaller animals that often get overlooked in discussions of Jurassic life were actually crucial to maintaining these balances. Insects processed enormous amounts of dead plant and animal material, recycling nutrients back into the soil where they could support new plant growth. Small mammals and reptiles consumed insects and other invertebrates, transferring energy from decomposer communities up to higher levels of the food web. Even death itself was part of the balance. When large dinosaurs died, their massive carcasses became temporary ecosystems that supported scavengers, decomposers, and the plants that grew in the nutrient-rich soil around them. Nothing was wasted in these efficient biological cycles. The seasonal rhythms that governed much of Jurassic life created predictable patterns of abundance and scarcity that species learned to navigate over evolutionary time. Animals timed their reproductive cycles to coincide with periods of maximum food availability, ensuring that energy-demanding activities like egg-laying and caring for young occurred when resources were most plentiful. Migration patterns developed that allowed animals to follow favorable conditions across vast distances. Some species may have had migration routes that covered thousands of miles, moving between breeding grounds, feeding areas, and refuge habitats as seasons and climate cycles demanded. The evidence for these complex behaviors comes from multiple sources in the fossil record. Trackways show us that many species moved in coordinated groups, with parallel paths indicating organized herd movements. Bone beds containing multiple individuals of the same species suggest that some dinosaurs lived and died together, possibly in seasonal gathering areas or migration bottlenecks. Nesting sites preserved in the fossil record reveal sophisticated parental behaviors. Some dinosaur species built elaborate nests and may have cared for their young for extended periods. Eggs arranged in careful patterns suggest that parents understood the importance of temperature regulation and protection from predators. The preservation of these behavioral traces in rock tells us that the Jurassic world was not a simple collection of individual animals competing for resources, but a complex society where cooperation, communication, and social organization were just as important as size, strength, and speed. Feeding strategies became increasingly specialized as competition intensified. Different species of herbivorous dinosaurs evolved different approaches to processing plant material, allowing them to coexist in the same habitats without directly competing for identical resources. Some became high browsers, others specialized in ground-level vegetation, and still others developed the ability to process tough, fibrous plant parts that other species couldn't digest. This specialization created intricate webs of interdependence. A forest that lost its high-browsing sauropods might see changes in canopy structure that affected the plants growing below, which in turn influenced the herbivores that depended on ground-level vegetation, which ultimately affected the predators that hunted those herbivores. Predator specialization was equally sophisticated. Some theropods developed into pursuit predators with long legs and lightweight builds, perfect for chasing down fast-moving prey across open ground. Others became ambush specialists with powerful jaws designed for delivering devastating attacks to unsuspecting victims. Still others evolved into generalists that could switch between different hunting strategies depending on available opportunities. The arms race between predators and prey drove evolutionary innovations that we can still see in the fossil record. As predators became more sophisticated, Prey species developed better defenses. As defensive adaptations became more effective, predators evolved new strategies to overcome them. This constant evolutionary pressure kept both sides adapting and improving over millions of years. Camouflage and warning coloration may have been important survival strategies, though these soft tissue features are rarely preserved in fossils. Some dinosaur species may have had elaborate color patterns that help them blend into their environments or communicate with members of their own species. The chemical warfare that characterizes some modern ecosystems may have existed in the Jurassic as well. Some plants may have produced toxins to deter herbivores, while some animals may have evolved immunity to these compounds or even the ability to concentrate plant toxins in their own tissues as defense against predators. Communication systems in Jurassic animals were probably highly developed, though we can only infer their existence from anatomical features preserved in fossils. The complex nasal passages found in some dinosaur species suggest they could produce a wide range of sounds for communication. The elaborate crests and horns of many species may have been used for visual displays, as well as physical defense. Territory marking and recognition systems would have been essential for species that lived in complex social groups. The ability to distinguish between members of your own group and potential competitors or threats would have been crucial for survival in ecosystems where mistaken identity could be fatal. The evidence suggests that many Jurassic animals had cognitive abilities that were more sophisticated than we might expect from creatures that lived so long ago. Problem-solving skills, memory, and even basic reasoning may have been necessary for navigating the complex social and ecological challenges of their world. Tool use, while rare in the fossil record, may have been more common than we realize. Some theropods may have used rocks to break open tough shells or bones, while some herbivores may have used branches or other objects to access food sources that were otherwise out of reach. The learning abilities of young dinosaurs were probably highly developed, given the complex environments they had to master. Juvenile dinosaurs would have needed to learn not just what to eat and what to avoid, but also how to recognize predators, how to communicate with their own species, and how to navigate seasonal changes in resource availability. Parental care in many dinosaur species appears to have been extensive, with adults not just protecting eggs and hatchlings, but actively teaching young animals the skills they needed for survival. This investment in offspring education would have been crucial for species living in rapidly changing environments, where inflexible instincts might not be sufficient for survival. The social complexity of Jurassic ecosystems extended beyond individual species to include interspecies relationships that we're only beginning to understand. Some small dinosaurs may have followed herds of larger herbivores, feeding on insects disturbed by their movement. Some predators may have formed temporary alliances when pursuing particularly large or dangerous prey. Cleaning relationships, where small animals remove parasites from larger ones, may have been common in ecosystems where long-lived, large-bodied animals would have been particularly vulnerable to parasite loads. The mutual benefits of such relationships would have made them evolutionarily stable over long periods. These intricate relationships created ecosystems that were far more than simple collections of competing individuals. They were integrated communities where the success of each species depended on the health of the whole system, and where disruption to any one component could have cascading effects throughout the entire network. Understanding these relationships helps us appreciate why Jurassic ecosystems were so successful for so long, and why their eventual transformation at the end of the period required such dramatic environmental changes. The stability of these ancient communities was built on millions of years of coevolution and adaptation, creating bonds between species that were not easily broken. The legacy of these Jurassic relationships can still be seen in modern ecosystems, where similar patterns of cooperation, competition, and coevolution continue to shape the natural world. The principles that governed life 150 million years ago are still operating today, reminding us that despite all the changes our planet has experienced, the fundamental rules of ecology remain constant. As we prepare to conclude our journey through this remarkable period, we'll explore how the innovations and relationships that first appeared in the Jurassic world continue to influence life on Earth today, and what lessons this ancient world can teach us about the resilience and adaptability of life itself. The preservation of this incredible world in the fossil record represents one of the greatest detective stories in the history of science. Every fossil tells us something about how these ancient ecosystems functioned, but it takes careful analysis and interpretation to reconstruct the full picture of Jurassic life from the fragmentary evidence that has survived. The process of fossilization is itself a story of incredible odds. For every organism that became a fossil, millions more disappeared without a trace, their remains scattered by scavengers, decomposed by bacteria, or destroyed by geological processes. The fossils we do have represent only a tiny fraction of the life that once filled Jurassic landscapes. Yet from this limited evidence, paleontologists have been able to reconstruct not just what these ancient creatures looked like, but how they lived, what they ate, how they moved, and even how they interacted with each other and their environment. Each new fossil discovery adds another piece to this vast puzzle, sometimes confirming existing theories, and sometimes forcing us to completely rethink our understanding of ancient life. The technology used to study these fossils has revolutionized our ability to extract information from ancient remains. CT scans can reveal the internal structure of fossilized skulls, showing us details about brain size and sensory capabilities. Chemical analysis of fossil bones can tell us about diet, migration patterns, and even body temperature. Computer modeling can help us understand how extinct animals moved and behaved. This technological revolution has revealed that Jurassic life was far more complex and sophisticated than earlier generations of scientists could have imagined. We now know that many dinosaurs had feathers, that some were warm-blooded, that many lived in social groups, and that their behaviors were often as complex as those of modern animals. The geographic distribution of Jurassic fossils tells its own story about how life spread across the ancient world. Fossils of closely related species found on different continents provide evidence for the breakup of Pangaea and the drifting of continents. The appearance of new species in the fossil record often coincides with geological events that created new habitats or barriers to migration. Marine fossils are particularly valuable for understanding global patterns because ocean currents could distribute marine organisms across vast distances. The presence of similar ammonite species in rocks from different continents tells us that ocean connections existed between regions that are now separated by thousands of miles. The quality of fossil preservation varies dramatically depending on the environment where organisms died and were buried. The finest details are preserved in environments where burial was rapid and decay was prevented, such as volcanic ash deposits or fine-grained sediments in quiet water bodies. These exceptional preservation sites provide windows into ancient life that are almost like photographs taken millions of years ago. Some fossils preserve not just bones and shells, but also soft tissues, skin impressions, and even evidence of behavior such as bite marks, pathologies, and healed injuries. These details help us understand not just what these ancient creatures looked like, but what their lives were actually like. The study of coprolites, fossilized feces, provides direct evidence of what extinct animals ate and how their digestive systems functioned. These unglamorous fossils can contain remarkably well-preserved plant and animal remains that tell us about food webs and ecological relationships with a precision that's impossible to achieve from bones alone. Trace fossils, such as footprints, burrows, and bite marks, preserve evidence of behavior rather than anatomy. These fossils can tell us how fast animals moved, whether they lived in groups, how they interacted with their environment, and even details about their daily activities that would otherwise be lost to time. The temporal distribution of fossils allows us to track evolutionary changes over time and understand how ecosystems responded to environmental changes. The appearance and disappearance of species in the fossil record provides a timeline of evolutionary innovation and extinction that spans millions of years. This fossil evidence has revealed that the Jurassic was a time of remarkable evolutionary experimentation, when life was testing new strategies and exploring new possibilities with a creativity that's rarely matched in Earth's history. The innovations that first appeared during this period would go on to influence the course of evolution for hundreds of millions of years. The birds flying outside your window today carry genetic blueprints that were first sketched out in the bodies of small Jurassic theropods. The flowers blooming in your garden use reproductive strategies that were pioneered by Jurassic gymnosperms. The ecosystems that surround us operate according to principles that were first established in ancient Jurassic communities. This continuity between past and present reminds us that we are not separate from the natural world, but part of an ongoing story that began billions of years ago and continues to unfold around us every day. The Jurassic period was not an isolated chapter in Earth's history, but a crucial link in the chain of life that connects the earliest organisms to the complex ecosystems of today. Understanding this connection helps us appreciate both the antiquity and the modernity of life on Earth. The same forces that shaped Jurassic ecosystems, competition and cooperation, adaptation and extinction, innovation and conservation, continue to operate in the world around us. The lessons learned from studying this ancient world remain relevant for understanding how life responds to environmental change and how ecosystems maintain their stability in the face of constant challenges. The Jurassic period ultimately teaches us that life is both incredibly resilient and remarkably creative. Given the right conditions, living organisms can evolve into forms that stretch the limits of what seems possible, creating giants that dwarf anything alive today and ecosystems of breathtaking complexity and beauty. But it also teaches us about the importance of environmental stability for supporting such complexity. The greenhouse conditions that characterize the Jurassic provided a stable foundation that allowed ecosystems to develop intricate relationships and support enormous biodiversity over tens of millions of years. The end of the Jurassic period would eventually come, brought about by environmental changes that challenged even these remarkably adaptable ecosystems. But the legacy of this incredible time would live on in the descendants of Jurassic organisms and in the ecological principles that they helped establish. As we conclude our journey through this fascinating period, we carry with us a deeper appreciation for the complexity and beauty of ancient life, and a better understanding of our place in the grand story of evolution that connects us to every creature that has ever lived on our remarkable planet. The preservation of soft tissues in some exceptional Jurassic fossils has revolutionized our understanding of how these ancient creatures actually looked and functioned in life. When paleontologists discovered fossilized skin impressions showing that some dinosaurs had intricate patterns of scales, or when they found evidence of primitive feathers on small theropods, it completely changed how we visualize these animals. But perhaps the most remarkable discoveries have come from studying the internal anatomy preserved in some fossils. CT scanning technology has allowed scientists to peer inside fossilized skulls and see the actual brain cavities of dinosaurs that died 150 million years ago. What they found is surprising. Many of these ancient creatures had brain-to-body ratios that were much higher than previously thought, suggesting levels of intelligence and behavioral complexity that rival modern birds and mammals. The inner ear structures preserved in some fossils tell us about how these animals heard and balanced themselves. Some dinosaurs had inner ears that were perfectly adapted for detecting low-frequency sounds, which supports the idea that they communicated using deep, rumbling calls that could travel for miles across ancient landscapes. Even more fascinating are the discoveries related to metabolism and physiology. Bone histology, the study of bone tissue under microscopes, has revealed that many Jurassic dinosaurs had bone growth patterns that are more similar to warm-blooded mammals than to cold-blooded reptiles. This suggests that the giants of the Jurassic were not sluggish, cold-blooded creatures waiting for the sun to warm them up, but active, dynamic animals with metabolisms that could support constant activity. The implications of this are staggering. If dinosaurs were indeed warm-blooded, or at least somewhere between warm and cold-blooded, then they would have required enormous amounts of food to fuel their metabolism. A warm-blooded Allosaurus would have needed to consume far more prey than a cold-blooded one, which would have dramatically affected predator-prey ratios and ecosystem dynamics. This metabolic revolution also explains how some dinosaurs could thrive in environments that would challenge purely cold-blooded animals. The polar regions during the Jurassic, while warm by today's standards, still experience seasonal variations in daylight that would have made life difficult for animals that depended entirely on external heat sources. The discovery of melanosomes, cellular structures that produce pigments, in some Jurassic fossils has even allowed scientists to determine the actual colors of extinct animals. We now know that some small theropods had iridescent black feathers similar to modern ravens, while others had reddish-brown plumage with distinctive patterns. These color reconstructions aren't just academic curiosities. They tell us about behavior, ecology, and evolution in ways that bone structure alone never could. Bright colors might indicate sexual display behaviors, while camouflage patterns suggest specific habitat preferences and predator avoidance strategies. The study of growth series, fossils of the same species at different life stages, has revealed that many Jurassic animals underwent dramatic changes as they matured. Some species that were once thought to be different dinosaurs entirely turned out to be juvenile and adult forms of the same animal, just with such different proportions and features that they were unrecognizable. This discovery has profound implications for understanding dinosaur behavior and ecology. If young animals looked and behaved very differently from adults, then different age groups might have occupied completely different ecological niches, reducing competition between parents and offspring, while maximizing the resources available to each species. The social implications of these discoveries are equally fascinating. Evidence suggests that many dinosaur species had complex family structures, where adults cared for young for extended periods. Some fossils show adults and juveniles buried together, suggesting family groups that stayed together even in death. Nesting sites preserved in the geological record reveal sophisticated parental behaviors. Some dinosaurs built elaborate nests with carefully arranged vegetation that would have generated heat through decomposition, providing stable temperatures for developing eggs. Others show evidence of communal nesting, where multiple individuals contributed to shared nesting areas. The discovery of embryos inside fossilized eggs has provided unprecedented insights into dinosaur development. These tiny fossils show us how baby dinosaurs grew inside their eggs, what they looked like when they hatched, and even how their proportions changed as they developed. Some embryos show evidence of advanced development at hatching, suggesting that they were born ready to follow their parents and fend for themselves. But not all discoveries paint a picture of peaceful family life. Bite marks on juvenile bones, sometimes matching the teeth of adults of the same species, suggest that cannibalism may have been more common than we'd like to imagine. In times of stress or resource scarcity, even social species might have resorted to eating their own kind to survive. The preservation of stomach contents in some fossils provides direct evidence of what these animals actually ate, moving beyond educated guesses based on tooth shape to concrete proof of dietary preferences. These discoveries have sometimes overturned long-held assumptions about feeding behaviors and ecological roles. Gastroliths, or stomach stones, found with dinosaur skeletons tell us about digestive strategies that were crucial for processing tough plant material. The size, shape, and wear patterns of these stones provide clues about how different species process their food and how efficient their digestive systems were. The distribution of these fossil discoveries across the globe tells its own story about how Jurassic ecosystems were connected and how they varied from place to place. While the basic principles of predator-prey relationships and ecological balance were consistent worldwide, local conditions created unique variations that we can still detect in the fossil record. Some regions show evidence of seasonal migrations on scales that dwarf anything we see in the modern world. Trackways stretching for hundreds of miles suggest that some dinosaur herds undertook journeys that would have taken them across multiple climate zones and through drastically different habitats. Other areas show evidence of more stable, resident populations that remained in the same general areas year-round. These differences in mobility strategies reflect adaptations to local environmental conditions and resource availability, showing that Jurassic animals were just as behaviorally flexible as modern species. The preservation of these migration routes in rock formations allows us to trace the movements of individual herds across ancient landscapes. In some cases, we can follow the same group of animals for hundreds of miles, watching as their footprints tell the story of their journey through changing terrain and varying conditions. These discoveries have transformed our understanding of Jurassic ecosystems from simple collections of individual animals into complex, interconnected communities where behavior, physiology, and ecology were intimately linked. Every new fossil adds another piece to this puzzle, revealing layers of complexity that continue to surprise and amaze scientists. The technological advances that make these discoveries possible are accelerating at an unprecedented rate. New imaging techniques, chemical analysis methods, and computer modeling capabilities are revealing details about ancient life that would have been impossible to detect just a few decades ago. Synchrotron radiation, one of the most powerful tools in modern paleontology, can reveal the internal structure of fossils without damaging them, showing us details down to the cellular level. This technology has revealed preserved blood vessels, nerve tissues, and even possible cellular structures in fossils that are hundreds of millions of years old. Isotope analysis of fossil bones and teeth can tell us about diet, migration patterns, climate conditions, and even seasonal behaviors. By analyzing the chemical signatures locked in ancient tissues, scientists can reconstruct environmental conditions with precision that would have seemed impossible just a generation ago. These advances are not just improving our understanding of individual species, but are revolutionizing our comprehension of entire ecosystems and how they functioned. We can now track energy flow through ancient food webs, understand predator-prey dynamics with quantitative precision, and even detect evidence of diseases and parasites that affected Jurassic life. The integration of all this evidence is painting a picture of the Jurassic world that is far more vivid and detailed than anything previous generations of scientists could have imagined. These weren't just collections of strange, extinct creatures, but functioning ecosystems with all the complexity, beauty, and interconnectedness that we see in the natural world today. This new understanding carries profound implications for how we think about evolution, extinction, and the future of life on Earth. The Jurassic shows us that life is capable of incredible innovation and adaptation when given stable environmental conditions over long periods of time. But it also shows us how even the most successful ecosystems can be vulnerable to rapid environmental change. The lessons we're learning from studying Jurassic life are directly relevant to understanding how modern ecosystems might respond to current environmental challenges. The same principles that governed ancient food webs and ecological relationships continue to operate today, even though the players have changed. As we continue to unlock the secrets hidden in Jurassic rocks, we're not just learning about the past, we're gaining insights that could help us better understand and protect the natural world that surrounds us today. The story of the Jurassic is ultimately our story too, part of the continuous thread of life that connects us to every creature that has ever lived on this remarkable planet. The incredible journey we've taken through this ancient world reveals that Earth's history is not a series of disconnected chapters, but a continuous story of adaptation, innovation, and survival that spans hundreds of millions of years. The giants that once walked among towering forests of conifers and ferns have left us more than just bones and footprints. They've left us a legacy of understanding about how life responds to challenge and opportunity. The Jurassic period stands as one of the most successful experiments in the history of life on Earth, a time when stable environmental conditions allowed evolution to explore possibilities that seem almost limitless in their scope and creativity. From the smallest feathered dinosaur taking its first tentative flight to the massive sauropods that reshaped entire landscapes just by feeding, this ancient world demonstrates the incredible potential of life when given the right conditions to flourish. As we continue to study and learn from these ancient ecosystems, we carry forward not just scientific knowledge, but a deeper appreciation for the complexity, resilience, and beauty of the natural world that continues to evolve around us today. The interconnected web of relationships that defined Jurassic ecosystems becomes even more remarkable when we consider how death itself became part of the cycle of renewal. When one of those massive sauropods finally reached the end of its incredible lifespan, its death created opportunities that rippled through the entire community of life around it. Picture a diplodocus, perhaps 80 feet long and weighing as much as several modern elephants, taking its last breath beside a river in what would one day become the American West. Within hours, the scent would begin to attract scavengers from miles away. But this wasn't just a feeding frenzy. It was the beginning of an ecological event that could sustain life for months. The first to arrive would be the smaller theropods, agile predators no bigger than wolves that could dart in and out, claiming choice portions before larger competitors arrived. Their sharp teeth and quick movements allowed them to exploit opportunities that the massive predators couldn't access. These weren't failed giants, they were successful specialists, perfectly adapted for their role in the ecosystem. Following close behind would come the true giants of predation. An Allosaurus approaching such a bounty wouldn't need to risk the dangers of hunting live prey. Here was protein enough to sustain it for weeks, and the only competition came from other scavengers rather than defensive herbivores with deadly tail spikes or crushing feet. But the ecosystem's cleanup crew extended far beyond the obvious predators. Insects would arrive in clouds, their larvae processing soft tissues with an efficiency that no vertebrate could match. Within days, the carcass would be alive with millions of tiny recyclers, each playing their part in breaking down complex organic molecules into simpler compounds that could feed the soil. Even the plants participated in this cycle of renewal. The massive amount of nutrients released by decomposition would create a zone of incredibly rich soil around the carcass. Seeds that had passed through the dinosaur's digestive system during its final meals would find themselves in perfect growing conditions, surrounded by more fertilizer than they could ever use. Within a year, the spot where the giant had fallen would be marked by a patch of unusually lush vegetation. Ferns would grow larger and greener. Cycads would develop more robust trunks and fuller crowns, and young conifers would shoot upward at accelerated rates. The death of one giant had become the foundation for an explosion of plant life that would support countless other organisms. This pattern of death and renewal was happening constantly across Jurassic landscapes. Every fallen tree, every unsuccessful hunt, every natural death became an opportunity for other forms of life to flourish. Nothing was wasted in these efficient biological systems, and energy flowed from one form to another with a completeness that modern ecosystems rarely achieve. The seasonal rhythms that governed much of this activity were driven by climate patterns that operated on scales both local and global. The monsoon-like weather systems that brought months of torrential rain followed by months of drought created pulses of growth and dormancy that affected every living thing. During the wet seasons, rivers would swell beyond their banks, carrying nutrients across vast floodplains and creating temporary wetlands that supported explosion of life. Amphibians would emerge from hiding places to breed in temporary pools. Insects would multiply in the humid conditions. Plants would grow with unprecedented vigor in the warm, moist air. These seasonal floods also redistributed the products of decomposition across entire landscapes. Nutrients that had been locked up in dead plant and animal matter would be dissolved and carried by flowing water to new locations, sometimes hundreds of miles away. A tree that died in the mountains might ultimately contribute to the growth of ferns in coastal wetlands through this vast circulatory system of seasonal flooding. The dry seasons brought different challenges and opportunities. As water levels dropped and vegetation withered, herbivores were forced to concentrate around the remaining water sources. These seasonal gatherings created temporary communities where species that might otherwise rarely encounter each other were brought together by necessity. Fossil evidence suggests that some of these seasonal gatherings were enormous, with trackways showing hundreds of individual animals converging on ancient waterholes. The social dynamics of these meetings must have been incredibly complex, with different species working out hierarchies of access to the precious remaining resources. Predators learn to time their activities around these predictable gatherings. Why exhaust yourself hunting scattered prey across vast territories when the dry season would concentrate your targets around a few reliable water sources? This seasonal strategy required predators to be patient and strategic, waiting for the right moment to strike when prey animals were most vulnerable. The evolutionary pressure created by these seasonal cycles drove innovations in water conservation, food storage, and migration strategies. Some dinosaurs may have developed the ability to store fat during abundant times to sustain them through lean periods. Others may have evolved enhanced sensory capabilities that allowed them to locate hidden water sources or detect the first signs of seasonal change. Plant communities also adapted to these extreme seasonal variations. Deep root systems that could tap groundwater during dry periods became essential for survival. Specialized storage organs developed that could hold water and nutrients through months of drought. Reproductive cycles were timed to take advantage of seasonal rains, with seeds germinating en masse when conditions were optimal. The interaction between these seasonal cycles and the ongoing geological activity of the Jurassic created patterns of environmental change that were both predictable and unpredictable. While animals and plants could adapt to regular seasonal variations, volcanic eruptions and earthquakes added elements of chaos that kept ecosystems dynamic and prevented any single species from becoming too dominant. These geological disruptions, while destructive in the short term, actually contributed to the long-term stability of Jurassic ecosystems by preventing competitive exclusion and maintaining habitat diversity. A volcanic eruption that destroyed a forest in one area would create opportunities for pioneer species to establish new communities, while the nutrients released by weathering volcanic rock would eventually support more diverse plant communities than had existed before. The ability of Jurassic life to recover from these disruptions demonstrates a level of ecological resilience that we rarely see in modern ecosystems. This resilience was built on redundancy, with multiple species capable of filling similar ecological roles, and on flexibility, with individual species capable of adapting their behaviors and strategies to changing conditions. The success of this approach is evident in the longevity of Jurassic ecosystems. For over 50 million years, these communities maintained their basic structure while continuously evolving and adapting to new challenges. This represents one of the longest periods of ecological stability in Earth's history, and it occurred during a time of dramatic geological and climatic change. Understanding how these ancient ecosystems achieved such remarkable stability has profound implications for conservation biology and ecosystem management today. The principles that allowed Jurassic communities to persist through millions of years of environmental change are still relevant for understanding how modern ecosystems respond to disturbance and how they might be protected in an era of rapid global change. The diversity that characterized Jurassic ecosystems wasn't just about the number of different species, but about the variety of ecological strategies and life histories that those species represented. This functional diversity meant that ecosystems could continue operating even when individual species disappeared, because other species could step in to fill vacant roles. This redundancy was particularly important for key ecological processes like decomposition, pollination, and seed dispersal. With multiple species capable of performing each function, the loss of any single species didn't create system-wide collapse. Instead, other species could expand their roles to compensate for the missing functionality. The modular structure of Jurassic ecosystems also contributed to their stability. Rather than being tightly integrated systems where every species depended on every other species, these communities were organized into loosely connected modules that could function semi-independently. This meant that disruptions in one part of the system didn't necessarily cascade throughout the entire community. This modular organization is evident in the fossil record, where we see different assemblages of species associated with different habitat types. Forest communities had their own characteristic species, while open plain communities supported different assemblages, and wetland communities had their own unique combinations of plants and animals. The boundaries between these habitat modules were often gradual rather than sharp, creating transition zones where species from different communities could interact and exchange resources. These edge habitats were often particularly diverse, supporting species from multiple communities, as well as specialists that were adapted specifically to these transitional conditions. The mobility of many Jurassic species also contributed to ecosystem stability by allowing genetic exchange between populations and providing rescue effects when local populations crashed. The trackway evidence showing long-distance movements by dinosaur herds suggests that gene flow was maintained across vast geographic distances, preventing local populations from becoming genetically isolated and vulnerable to extinction. This connectivity between distant populations meant that Jurassic ecosystems were organized at continental and even global scales. Species that appeared to be locally rare might actually be part of much larger, widespread populations that were connected by seasonal migrations or occasional long-distance dispersal events. The implications of this continental-scale organization are still being explored by paleontologists, but it appears that Jurassic ecosystems may have been among the most highly connected biological systems in Earth's history. The combination of stable climate conditions, continuous habitat corridors, and highly mobile species created opportunities for genetic and ecological exchange that are difficult to achieve in more fragmented modern landscapes. This high level of connectivity also facilitated the rapid spread of evolutionary innovations across vast distances. Beneficial adaptations that appeared in one population could quickly spread to others through gene flow, while new species that evolved in one region could rapidly colonize similar habitats thousands of miles away. The fossil record provides evidence for this rapid spread of innovations in the form of similar adaptations appearing simultaneously in widely separated geographic regions. The evolution of flight in dinosaurs, for example, appears to have occurred in multiple locations at roughly the same time, suggesting that the basic requirements for this adaptation were present throughout the Jurassic world. This pattern of parallel evolution occurring across multiple continents demonstrates that Jurassic ecosystems were not just locally stable, but were organized according to consistent principles that operated on a global scale. The same ecological relationships and evolutionary pressures that shaped life in one region were also operating in distant areas, creating similar solutions to similar challenges. The study of these global patterns in Jurassic ecosystems has revealed fundamental principles about how evolution and ecology interact on large spatial and temporal scales. These insights are helping scientists understand how biological systems respond to environmental change and how evolutionary innovations spread through populations and across landscapes. As we continue to uncover new evidence about the organization and function of Jurassic ecosystems, we're gaining a deeper appreciation for the sophistication and complexity of these ancient biological systems. Far from being simple collections of competing individuals, these were highly organized, efficiently functioning communities that achieved levels of productivity and stability that remain impressive even by modern standards. The legacy of these remarkable ecosystems extends far beyond the fossils they left behind. The evolutionary innovations that first appeared during the Jurassic continue to influence life on Earth today, while the ecological principles that govern these ancient communities provide insights that are directly relevant to understanding and protecting modern biodiversity. The technological revolution in studying these ancient ecosystems has revealed details that would have seemed impossible to detect just decades ago. When scientists first began using CT scanners on fossilized skulls, they weren't prepared for what they would find. Inside the bone cavities of creatures that had been dead for 150 million years, they discovered preserved evidence of brain structure, inner ear anatomy, and even blood vessel pathways that told stories about intelligence, hearing, and behavior that bones alone could never reveal. These discoveries have fundamentally changed how we understand the cognitive abilities of Jurassic life. The brain-to-body ratios of many dinosaurs were far higher than anyone had imagined, suggesting levels of problem-solving ability and social intelligence that rival modern birds and mammals. Some species had enlarged regions associated with spatial memory, which makes perfect sense for animals that needed to navigate vast territories and remember the locations of seasonal resources across continental scale ranges. The inner ear structures preserved in these fossils tell equally fascinating stories. Many dinosaurs had hearing systems that were specifically tuned to detect low-frequency sounds, the kind of deep, rumbling calls that could travel for miles across open landscapes. This suggests communication networks that operated on scales we can barely comprehend, with individual animals potentially coordinating their activities across distances that would span entire modern countries. But perhaps the most revolutionary discoveries have come from the microscopic analysis of fossilized bone tissue. When paleontologists began examining thin sections of dinosaur bones under high-powered microscopes, they found growth patterns that looked nothing like those of modern reptiles. Instead, they resembled the fast-growing, highly vascularized bone tissue of warm-blooded mammals and birds. This discovery has profound implications for everything we thought we knew about Jurassic life. If these animals were indeed warm-blooded, or at least had metabolisms somewhere between those of modern reptiles and mammals, then they would have been capable of sustained activity levels that would have completely transformed ecosystem dynamics. A warm-blooded predator could hunt actively throughout the day and night, while warm-blooded herbivores could maintain constant vigilance against threats. The energy requirements of warm-blooded metabolism would have been staggering for animals of such enormous size. A fully grown brachiosaurus with mammalian metabolism would have needed to consume something approaching a ton of vegetation every single day just to maintain its body weight. This helps explain how the lush plant communities of the Jurassic could support such massive animals, but it also suggests that these ecosystems were operating at levels of productivity that seem almost impossible by modern standards. Chemical analysis of fossilized bones has revealed even more surprising details about the lives of these ancient creatures. Isotope signatures locked in the mineral structure of teeth and bones can tell us about diet, migration patterns, and even seasonal behaviors with precision that rivals what we can achieve studying living animals. Some dinosaurs show isotopic evidence of long-distance migrations that would have taken them through multiple climate zones, while others appear to have remained in relatively small territories throughout their lives. The preservation of actual pigment structures in some fossils has allowed scientists to determine the real colors of creatures that died over 100 million years ago. We now know that some small theropods had iridescent black plumage that would have shimmered with rainbow colors in sunlight, while others displayed bold patterns of stripes and spots that may have been used for camouflage or species recognition. These color reconstructions aren't just curiosities. They provide crucial insights into behavior and ecology. Bright, conspicuous colors often indicate complex social behaviors and mate selection strategies, suggesting that Jurassic dinosaurs had rich social lives with elaborate courtship rituals and territorial displays. Camouflage patterns tell us about predator-prey relationships and habitat preferences with a specificity that skeletal anatomy alone could never provide. The discovery of preserved soft tissues in some exceptional fossils has opened entirely new windows into the physiology of ancient life. Fossilized blood vessels, nerve fibers, and even possible cellular structures have been found in bones that are hundreds of millions of years old. While the interpretation of these structures remains controversial, they represent an unprecedented opportunity to understand the biology of extinct organisms at the molecular level. Growth series studies, comparing fossils of the same species at different life stages, have revealed that many Jurassic animals underwent dramatic transformations as they matured. Some species changed so dramatically during development that juveniles and adults were initially classified as entirely different dinosaurs. These ontogenetic changes suggest complex life histories, where different age groups occupied completely different ecological niches, reducing competition between parents and offspring while maximizing the resources available to each species. The social implications of these developmental studies are particularly fascinating. Evidence suggests that many dinosaur species maintained family groups, where adults actively cared for and protected their young for extended periods. Some fossil sites preserve multiple generations buried together, suggesting multi-generational family structures that may have persisted for years or even decades. Nesting sites preserved in the geological record reveal sophisticated parental behaviors that rival those of modern birds. Some dinosaurs constructed elaborate nests with carefully arranged vegetation that would have generated heat through decomposition, providing stable incubation temperatures for developing eggs. Others show evidence of communal nesting, where multiple females contributed eggs to shared incubation sites that may have been guarded cooperatively. The preservation of embryos inside fossilized eggs has provided unprecedented insights into dinosaur development and early behavior. These tiny fossils show us exactly how baby dinosaurs grew inside their eggs, what they looked like when they hatched, and even how their body proportions changed during development. Some embryos show evidence of advanced development at hatching, suggesting that they were born ready to follow their parents and participate in complex social behaviors. But not all evidence points to peaceful family life. Bite marks on juvenile bones, sometimes matching the dental patterns of adults of the same species, suggest that cannibalism may have been a survival strategy during times of environmental stress. Even highly social species might have resorted to consuming their own young when resources became critically scarce. The preservation of actual stomach contents in some fossils provides direct, unambiguous evidence of what these animals ate, moving beyond educated guesses based on tooth shape to concrete proof of dietary preferences. These discoveries have sometimes completely overturned long-held assumptions about feeding behaviors and ecological roles, showing that the reality of ancient life was often far more complex than theoretical reconstruction suggested. Gastroliths, the polished stones found in association with many dinosaur skeletons, tell detailed stories about digestive strategies that were crucial for processing tough Jurassic vegetation. The size, shape, degree of polish, and mineral composition of these stones provide clues about how different species processed their food and how efficient their digestive systems were at extracting nutrients from fibrous plant material. The geographic distribution of these discoveries tells its own story about how Jurassic ecosystems were connected across vast distances. Trackway evidence shows migration routes that stretched for thousands of miles, with the same groups of animals following predictable pathways between seasonal feeding areas, breeding grounds, and refuge habitats. These continental-scale movements created connections between ecosystems that might otherwise have been isolated, facilitating gene flow and the spread of behavioral innovations across entire continents. Some regions show evidence of remarkable site fidelity, with multiple generations of the same species returning to identical locations year after year for decades or even centuries. These traditional gathering sites may have been passed down through generations via social learning, creating cultural traditions that persisted for thousands of years. The preservation of these ancient migration routes allows us to trace the movements of individual herds across changing landscapes, watching as their footprints tell stories of journeys through mountain passes, across river valleys, and along ancient coastlines. In some cases, we can follow the same group of animals for hundreds of miles, observing how their behavior changed as they moved through different habitats and encountered varying environmental conditions. These discoveries have transformed our understanding of Jurassic ecosystems, from collections of individual species into integrated communities where behavior, physiology, and ecology were intimately interconnected. Every new fossil adds another layer to this complex picture, revealing relationships and processes that continue to surprise researchers who thought they understood how these ancient worlds functioned. The pace of discovery is accelerating as new technologies become available and new fossil sites are explored. Synchrotron radiation facilities can now reveal the internal structure of fossils at the cellular level without damaging them, while mass spectrometry can detect trace elements and organic compounds that provide biochemical signatures of ancient life processes. Advanced computer modeling allows researchers to test hypotheses about how extinct animals moved, fed, and interacted with their environments. Biomechanical analyses can determine maximum running speeds, bite forces, and metabolic requirements with precision that approaches what we can achieve with living animals. Finite element analysis can show exactly how forces were distributed through dinosaur skulls during feeding, revealing feeding strategies and dietary preferences that wouldn't be obvious from simple anatomical observations. Climate modeling based on geological and paleontological evidence can reconstruct ancient weather patterns, seasonal cycles, and long-term environmental changes with remarkable accuracy. These reconstructions provide the environmental context needed to understand how ecosystems functioned and how they responded to changing conditions over millions of years. The integration of all these different types of evidence is creating an increasingly detailed and nuanced picture of Jurassic life that goes far beyond simple reconstructions of what these animals looked like. We're beginning to understand how they lived, how they interacted with each other and their environment, and how their behaviors and life strategies were shaped by the unique conditions of their time. This new understanding has profound implications for how we think about evolution, extinction, and the future of life on Earth. The Jurassic demonstrates that when environmental conditions remain stable for extended periods, evolution can explore possibilities that seem almost unlimited in their scope and creativity. But it also shows us how even the most successful adaptations can become vulnerabilities when conditions change rapidly. The lessons we're learning from these ancient ecosystems are directly relevant to understanding how modern life might respond to current environmental challenges. The same principles that govern Jurassic food webs, migration patterns, and species interactions continue to operate today, even though the specific players have changed dramatically. The incredible diversity and complexity of Jurassic life also provides hope for the future of evolution. Despite the challenges facing modern ecosystems, the fossil record shows us that life has an almost unlimited capacity for innovation and adaptation when given the opportunity to explore new possibilities. The giants of the Jurassic were not evolutionary accidents, but the predictable results of stable environmental conditions and abundant resources. As we continue to unlock the secrets preserved in ancient rocks, we're not just learning about the distant past. We're gaining insights that could help us better understand and protect the natural world that continues to evolve around us. The story of the Jurassic is ultimately our story too, part of the unbroken chain of life that connects every living thing on Earth to the ancient worlds that came before. The technological revolution that's transforming paleontology shows no signs of slowing down. Artificial intelligence is beginning to assist in the identification and analysis of fossils, while virtual reality is allowing researchers to explore ancient environments in ways that would have been pure science fiction just a few years ago. These tools are not just making research more efficient, they're revealing entirely new categories of information that were previously invisible. Molecular paleontology, the study of ancient proteins and DNA, is pushing the boundaries of what we thought was possible in terms of recovering biological information from very old fossils. While the recovery of actual DNA from Jurassic specimens remains highly controversial, proteins are proving to be much more stable over geological time, and their analysis is providing insights into evolutionary relationships and biological processes that complement traditional anatomical studies. The democratization of these technologies is also changing who can participate in paleontological research. High-resolution 3D scanning equipment that once cost hundreds of thousands of dollars is now available to universities and even amateur researchers, while online databases are making fossil collections accessible to scientists around the world. This explosion of accessibility and capability is accelerating the pace of discovery in ways that would have been impossible for previous generations of researchers. New species are being described at unprecedented rates, while existing specimens are being reanalyzed with techniques that reveal details that were missed in earlier studies. The cumulative effect of all these advances is creating a renaissance in paleontology that's fundamentally changing how we understand ancient life. The Jurassic world that's emerging from this research is far more complex, dynamic, and interconnected than anyone could have imagined, and each new discovery adds another layer to our appreciation of just how remarkable these ancient ecosystems really were. The integration of all these discoveries is revealing something profound about the nature of ancient ecosystems that goes beyond anything we could have imagined from studying isolated fossils. When we piece together the evidence from bone chemistry, growth patterns, behavioral traces, and environmental reconstructions, what emerges is a picture of biological communities that were operating according to principles we're only beginning to understand. The efficiency of energy transfer through Jurassic food webs appears to have been remarkably high, with minimal waste and maximum utilization of available resources. This wasn't just about individual species being well adapted to their environments. It was about entire ecosystems functioning as integrated systems where every component played a crucial role in maintaining the stability and productivity of the whole. Consider how nutrients moved through these ancient communities. When a massive sauropod died, its decomposition didn't just feed scavengers and decomposer organisms, it created a pulse of fertility that could be detected in plant growth patterns for years afterward. Chemical signatures from these nutrient pulses have been found in fossilized wood, showing how the death of individual giants rippled through entire forest communities. But the flow of nutrients wasn't limited to local effects. Seasonal migrations moved enormous quantities of organic matter across continental distances as herds of herbivores transported nutrients from their feeding grounds to their breeding areas and back again. This biological pump helped maintain soil fertility across vast regions and may have been crucial for sustaining the incredibly productive plant communities that characterized the period. The role of smaller organisms in maintaining these nutrient cycles was equally important, even if it's less obvious in the fossil record. Insects processing dead organic matter, soil microorganisms breaking down complex molecules, and countless other tiny recyclers working together created the foundation that supported everything else in the ecosystem. This multi-layered approach to resource utilization meant that Jurassic ecosystems could extract more energy and nutrients from their environment than most modern communities managed to achieve. Every niche was filled, every opportunity exploited, and every waste product became someone else's resource in an intricate web of interdependence that operated with clockwork precision. The temporal dynamics of these systems were equally sophisticated. Different species timed their life cycles to take advantage of seasonal abundance while avoiding periods of scarcity. Breeding seasons were coordinated not just with favorable weather, but with the availability of specific food resources that would be needed to support growing offspring. Some species appear to have had reproductive cycles that were synchronized with the fruiting or spore production cycles of their preferred plant foods. Others timed their breeding to coincide with seasonal insect emergences or the migrations of prey species. This temporal coordination created waves of biological activity that swept across landscapes in predictable patterns year after year. The fossil record preserves evidence of these temporal patterns in the form of growth bands in bones and shells, seasonal accumulations of particular fossil types, and even the preservation of mass mortality events that occurred during predictable environmental stress periods. These patterns show us that Jurassic life was organized not just in space, but in time, with different activities and life stages precisely timed to mesh with the rhythms of the environment. The communication networks that coordinated these complex behaviors must have been incredibly sophisticated. The evidence for long-distance acoustic communication in dinosaurs suggests that information could flow across enormous distances, allowing widely separated populations to coordinate their activities and respond collectively to environmental changes. Visual communication was equally important, with elaborate display structures, color patterns, and behavioral displays that could convey complex information about species identity, reproductive status, territorial boundaries, and threat levels. Some of the most ornate features we see in Jurassic fossils probably functioned as biological billboards, broadcasting information that was crucial for maintaining social order in complex communities. Chemical communication may have been even more widespread, though it's much harder to detect in the fossil record. Scent marking, pheromone trails, and chemical alarm signals could have created invisible information networks that helped coordinate group behaviors, warn of dangers, and maintain social hierarchies without the need for constant visual or acoustic contact. The sophistication of these communication systems suggests that many Jurassic animals had cognitive abilities that were far more advanced than we typically associate with extinct reptiles. Problem-solving skills, memory, learning ability, and even rudimentary forms of culture may have been more common than we realize, hidden in behavioral adaptations that left only subtle traces in the fossil record. Social learning appears to have been particularly important for species with complex life histories or extensive migration patterns. Young animals would have needed to learn not just basic survival skills, but also detailed information about seasonal timing, migration routes, food sources, and social protocols that would have been impossible to encode genetically. The evidence for extended parental care in many dinosaur species supports this interpretation, suggesting that adults invested significant time and energy in educating their offspring rather than simply protecting them from immediate dangers. This investment in education would have been crucial for maintaining cultural traditions that could persist across multiple generations. Some migration routes may have been cultural rather than instinctual, passed down through generations of social learning and maintained by group memory rather than genetic programming. The consistency of some trackway patterns across thousands of years suggests that certain pathways became traditional routes that were used repeatedly by successive generations of the same species. These cultural traditions may have been among the most vulnerable aspects of Jurassic ecosystems when environmental conditions began to change. Unlike genetic adaptations, cultural knowledge could be lost in a single generation if the chain of transmission was broken by environmental catastrophe or population crashes. The resilience of Jurassic ecosystems depended not just on biological diversity, but on this cultural diversity as well. Different populations of the same species may have maintained different behavioral traditions, creating a kind of cultural redundancy that provided backup strategies when primary approaches failed. The loss of this cultural knowledge may have been one of the factors that made recovery from environmental disruptions more difficult for some species than for others. Animals that depended heavily on learned behaviors would have been particularly vulnerable to population bottlenecks that broke the chain of cultural transmission. Understanding these cultural dimensions of ancient ecosystems adds another layer of complexity to our appreciation of how these systems functioned and how they responded to environmental change. It also highlights the importance of maintaining not just genetic diversity, but behavioral and cultural diversity in modern conservation efforts. The parallels between ancient and modern ecosystem dynamics become even more striking when we consider how Jurassic communities responded to environmental stress. During periods of climate change or geological disruption, these ancient ecosystems showed remarkable flexibility in reorganizing themselves to maintain basic functions, even when species composition changed dramatically. This flexibility was built on functional redundancy, with multiple species capable of performing similar ecological roles. When environmental changes eliminated some species, others could expand their roles to fill the vacant niches, maintaining ecosystem stability even as the cast of players changed. The modular organization of these ecosystems also contributed to their resilience. Rather than being tightly integrated systems where every species depended on every other species, Jurassic communities were organized into loosely connected modules that could function semi-independently. This meant that disruptions in one part of the system didn't necessarily cascade throughout the entire community. This modular structure is evident in the way different habitat types supported distinct assemblages of species, while still maintaining connections through mobile animals that moved between habitats. These connections allowed genetic exchange and resource sharing, without creating the tight interdependencies that could make entire systems vulnerable to cascade failures. The mobility of many Jurassic species was crucial for maintaining these connections and providing the flexibility needed to respond to environmental changes. When conditions in one area became unfavorable, populations could relocate to more suitable habitats, maintaining genetic diversity and preventing local extinctions from becoming global ones. This high level of connectivity between populations and habitats may have been one of the key factors that allowed Jurassic ecosystems to persist for such long periods despite ongoing environmental changes. The ability to redistribute populations in response to shifting conditions provided a kind of biological insurance against localized disasters. The fossil record shows us that this strategy was remarkably successful for tens of millions of years. But it also reveals the limitations of even the most resilient biological systems. When environmental changes became too rapid or too severe, even these highly connected and flexible ecosystems began to show signs of stress. From that first breath of humid Jurassic air to the thunderous footsteps of giants crossing ancient floodplains, we've witnessed a world that challenges everything we thought we knew about life on Earth. The Jurassic period wasn't just about enormous dinosaurs. It was about an entire planet operating as a finely tuned biological machine where every component, from the smallest insect to the most massive sauropod, played an irreplaceable role in maintaining the delicate balance that sustained life for over 50 million years. As we continue to unlock the secrets preserved in stone, we're reminded that understanding our planet's past isn't just about satisfying curiosity. It's about learning the principles that could help us protect and nurture the incredible diversity of life that continues to evolve around us today.